Okay guys, you have this problem called 13.80 in your Mastering Chemistry, and I know a lot of you are confused about it. Anyway, it says something like the activation barrier for hydrolysis of sucrose into glucose and fructose is 108 kilojoules per mole. If an enzyme increases the rate of the reaction by a factor of 1,000, I changed the number because I'm not solving this for you. I'm just showing you how you'd set it up. Anyway, how much lower does the activation barrier have to be when sucrose is in the active site? Assume the frequency factor for the catalyzed and uncatalyzed reactions are identical, and that the temperature is 298 Kelvin. Okay, so the activation barrier is actually just equal to the activation energy. And we actually know this equation. The rate equals the frequency factor. And I know Dr. Yang went into more detail, but for the other classes that might be watching this, they don't know that. But anyway, frequency factor times e to the negative EA over RT. So, without the enzyme, K1, which is what we're calling rate 1, is equal to A times e to the negative EA1 over RT. And it's very important that you guys label these in order to differentiate them. And then with the enzyme, K2 equals A times e to the negative EA2 over RT. Okay, and that's a division sign. I kind of messed up earlier. Anyway, so we have to set this up as a ratio. And what we do is K2 over K1 equals A times e to the negative EA2 over RT. And we do this because we want, we put K2 on top because it's easier to solve this way and it's less nightmarish algebra. So anyway, the larger one, the enzyme catalyzed one, or the something that has a catalyst, I always find it's easier to put it on top. So anyway, and that's over A to the negative A times e to the negative EA1 over RT. Okay, so a couple of things here. So up here, we were told we're assuming the frequency factor for both the catalyzed and uncatalyzed reactions are identical. So let's see. When we assume the reactions are identical, the frequency factor, which is the A, are the same. Okay, so we're able to cancel these A's. And that'll make life easier on you. So that moves us to here, where we just have E times negative EA2 over RT over E times negative EA1, E to the negative EA1 over RT. Okay, and we also know that the temperature is going to be 298 K and that we're going to use the same R. So this actually isn't going to be that bad. So then what we do, because they're both over the same R and the same T, we're able to combine these into a single expression because of the laws of logarithms. So it becomes e to the negative EA2 minus a negative EA over A1. Negative EA2 minus a negative EA1 over RT. So then I just made that pretty into EA1 minus EA2 over RT. Okay, so we can't forget that all equaled ln of K2 minus K1 equals EA1 over EA2 to the RT. And the reason that I did this is if we take the natural log of this ln, it undoes it and it just leaves it a fractional number. And then I had to take the logarithm of this side because you have to do that to both sides of the equation if you wanted to undo the e, or you're going to have a really hard time manipulating this. So now what we have is we know from here where it said that it was increased by a factor of 1,000 or 10,000 or 1,000,000 or whatever yours says. I chose 1,000. We know that K2 is 1,000 times K1 because it said it increased it by a factor of however many it said. So that just means that K2 is this many times K1. So that makes it easy to come here and substitute it in 1,000 times K1 over K1, and we're able to cancel the K1 over K1. Okay? And what I did in the meantime is I multiplied through the RT from this side to this side in order to make it easier to solve for this, which is what the problem wants. And it cancels the RT on that side, and it's on this side now. So R, you want the R that gives us the, the kilojoules over, let me see which one it wants us to use. Give me 1 second. I'm going to put down the phone really fast. Okay, so the R that we're using is 8.314 joules per mole Kelvin. We also know that the temperature from earlier, as mentioned in the problem, was given to us, and that was 298K. In my problem, it might be different in yours. Okay, so all you have to do is plug the R and the T in here and multiply it by the natural log of this, and you'll get this difference, and that should help you guys be able to solve that. I'm not going to finish it because you guys do need to be able to do this on your own, but I hope that helped.